Yes, thanks. Share your screen. When you are ready, please go ahead.
Okay, can everyone hear me? All good?
Yes, all good.
Okay, fantastic. So yes, great to share our recent work with everyone at their comfort of their home office or office. So my name is Guanran Zhang. I'm a postdoc from COPE, the University of Queensland. And last December in Blue Mountains, I talked about some of our recent work on fluorine benzoyl-thiazole-based fluorescent compounds and their excited state relaxation processes. But today, I would like to share some of the work that's carried out on structurally similar compounds, but for a different application, which is using the dicyanovinyl-based fluorescent sensors for dual mechanism amine detection. So for this work, I collaborated from our synthetic chemist Alex Yacht and Van from COPE. Oops, don't know why I do that, but yeah, and under the supervision of Professor Paul Bunn and Dr. Paul Shaw. And I'd like to acknowledge the DFT group for the funding. So just to give you an outline of what we're talking about. So first I'm introducing why we'd like to do amine detection before introducing the sensing compound we used and their responses with amines in solution. Based on what we find in solution, we propose the reaction mechanism, and then we move on to the solid state detection where we find the second mechanism. And these mechanisms being combined together demonstrate its potential application to be used in smart meat packaging. So to explain why we're interested in amine detection, I would like to first talk a little bit about food wastage. According to the United Nations, there's about 1.3 billion tons of food products being thrown away per year, which is due to the loss of food spoilage and transportation, which is equivalent to about $1 trillion US. And in Australia, this is about equivalent to every 1 in 5 shopping bags of food being thrown away in an average household. This is not just an economic issue, but also due to the huge demand of food due to wastage, we also have an over-farming, which leading to the global warming and land degradation, as well as overfishing, leading to the degraded marine ecosystem. To avoid these problems, one of the things we can do, especially on the consumer's end, is to detect the onset of food spoilage when the meat is just starting to go bad. Take, say, meat, for example. What we usually at home judge on whether this meat is off or not is very basic. We judge it by the color of it or the smell or the taste of it, which can be very objective. And also that when we notice something is wrong, probably this meat has already been off for quite a few days. So what we do to detect the early onset of meat spoilage is to detect the biogenic amines produced from the protein decomposition, which includes a series of amines just like putrescine, cadaverine, histamine, most of which are primary amines. So ideally, in order to be able to know whether the meat is starting to spoil or not at home, we want a detection device to first allow direct observation that we can clearly see by the change of something. And also we want this detection to be in a non-contact, non-invasive way, which means that we don't really have to cut off a piece of meat to know whether it's gone bad or not. So currently in literature, there are two mainstream detection methods that's being used. The first one is the colorimetric detection, which the name of which clearly suggests that, by using a chromophore, which can react with the target analyte, we have a change in the absorption spectrum, which gives you a change in the color of the compound itself. Well, the advantage of this colorimetric detection is very obvious, where you can directly see the change in color. One of the major problems as well is that the change in color sometimes can be very subtle. This is because colorimetric detection is based on chemical reactions, which can be slow in some cases, especially when the analyte concentration is low. And in these cases, the change in color can be very subjective to who's observing it. And the other detection mechanism is to use a fluorescence-based detection, in which people monitor the change in PL in either the PL spectrum or in PL intensity. One of the advantages for using fluorescence-based detection is that, say, when we have PL quenching, this quenching is much faster than chemical reaction, thus allowing the change in the PL intensity to be observed within a matter of seconds, as we can see in the right figure here. Ideally, what we want is a detection method that is first, very fast, and second, allow direct observation. So what we try to develop is sensing compounds that enable both colorimetric detection and fluorescent-based detection. So these are the sensing compounds that we use in this study. These are two isomeric molecules, both containing the fluorine and benzyl thiazole groups. The only difference in these molecules is that for K12 on the left-hand side here, the dicyanovinyl group is attached to the benzyl thiazole, whereas for K12B on the right-hand side, the dicyanovinyl group is attached to the fluorine compound, to the fluorine group. And the absorption and PL spectrum of K12 and K12B in both solution and solid state are shown in the figures below. We also measured the PLQI of these compounds in both solution and solid state, where for K12, we have a reasonably high PLQI of about 40% in both solution and solid state, whereas for K12B, the PLQI is relatively low. We see a 1% PLQI in solution and 4% PLQI in the solid state. So before we move on, the target analyte we chose is cadaverine, shown on the right-hand side here. The reason we chose cadaverine is basically two reasons. First is that it's a commonly used meat spoilage indicator that's adapted in food industry. This is because in fresh meat, the concentration of cadaverine is actually very low, it's negligible. Whereas once the spoilage process starts within a matter of 3 to 4 days, the concentration of cadaverine increases quite significantly. This allows us to monitor the quality of meat and to detect the release of cadaverine at the very early stage. Another reason that we use cadaverine is that, why did I do that again? The other reason why we use cadaverine is that it's also a representative analyte for a range of other primary amines. So first what we did is we add 5 equivalent molar of cadaverine into the solution of K12 and K12B in dichloromethane at a concentration of 10 micromolar. What we observed immediately after adding cadaverine is that we noticed a rapid decrease in the absorption peak in K12 within the first 30 minutes, accompanied by a blue shift of the absorption peak. Similar observations are also made with K12B, where we see a decrease in the preceding compound's absorption peak, followed by a blue shift in the peak itself. However, we did know that for K12B, the change in the spectrum is relatively slower comparing to K12, where after adding the cadaverine into the solution for 1 week, we still observe a slight change in the absorption. And when we monitor the PL spectrum by exciting at the preceding compound's absorption peak wavelengths, we notice a rapid decrease in PL intensity for K12, accompanied by a blue shift in the PL wavelength, PL spectrum, sorry. Whereas for K12B, when we excite at the peak absorption around 400 nanometers, what we observe in this case is that a gradual increase in the PL intensity, followed by a weak redshift. The increase in PL intensity is actually quite significant for K12B, where after overnight reaction, we have an over 10-fold increase in the peak intensity of the K12B compound. The change in the absorption spectrum, the blue change, accompanied by the shift in the PL spectrum and the change in PL intensity, first proved that these compounds might be suitable for what we want to do, which contains both colorimetric change characteristics and the change in PL intensity. But also what we found is that these features suggest that there is a change in the chromophore structure, which might be caused by a chemical reaction. Before we move on further to the chemical reaction mechanism, we want to know whether this change in the spectrum is universal to other primary amines. So we tested against a list of different primary amines, including butylamine, hexylamine, cadaverine, and ethylene diamine. And And to control the reactions, what we did is that, oops, why does it do that? Sorry. To normalize the concentration of different amines, what we did is that we add in the same concentration of amine groups into the solution. What this means is that we add in 10 equivalents of butylamine and hexylamine, whereas 5 equivalents of styrene and ethylene diamine is being added. And the first thing we notice is that, okay, let's see. So the first thing we did notice is that the change in, sorry, just give me a second. The first thing we noticed is that the change in absorption and PL spectrum is quite universal for all these amines. A blue shift in the absorption and the blue shift and decrease in PL intensity for K12, and the PL intensity increase in red shift for K12B is being observed for all these different amines. And as we're adding in amines in an excessive concentration, in an excess, the reaction themselves can be considered pseudo first order, which means that the change in PL intensity should follow should be exponentially dependent over time. And when we plot the change in PL intensity as a function of time, this is indeed what we observed. And we can fit these kinetics to an exponential function where we get the reaction rate constant as shown in the table here. So from these extracted rate constants, we observe a number of things. First, we notice that the reaction rate for K12 is consistently higher for K12B, which can be understood because if for K12, the dicyanovinyl group is being attached to benzyl thiazole, which makes it more electrophilic. And we also noticed that the reaction rate for the diamines are actually faster comparing to the monoalkyl amines. And while the exact mechanism is not very clear, what we think is happening is that there's an electrostatic interaction between the amine group and the cysteine compound. And in the case of monoalkyl amines, when the amine group is being electrostatic binded to the cysteine compound, the reaction rate would be hindered. Whereas in the case for diamines, when one of the amine groups is being electrostatically binded to the cysteine compound, there's another free amine group to react. So based on the observations we have established before, the reaction mechanism is proposed in this figure here. So here we used N-butylamine as the example amine, as all the reaction mechanisms we observe are very similar. So what we think is happening is that upon the presence of amine group, we have a Michael addition onto the vinyl bond here, forming this tetrahedral intermediate. And by forming this intermediate, we have a shortening of the pi conjugation, so it's giving us the blue shift in the absorption spectrum for both K12 and K12B. And because we have amine in excess, in the end, what we have is the release of malonyl and forming this imine compound, as shown here for both K12 and K12B. To examine whether this is indeed what's happening in the solution mixtures, what we did is we independently synthesized the proposed reaction products 1 and 2 from a different synthetic route from the aldehydes, and we compare the spectrum of the synthesized reaction product to the overnight mixture of K12 and K12B with butylamine. So by comparing the NMR spectrum, what we notice is that between the mixture solution and the synthetic product, very similar NMR spectrum are observed, which suggests that in the overnight mixture, indeed, we have this imine compound being present. Then we further moved on to compare the absorption and PL spectrum between the overnight mixture and the synthesized product. And we observed very similar absorption spectrum between the overnight mixture and the imine product here for K12. And when we measure the PL spectrum, we noticed that the overnight mixture can be fitted very well into 2 separate peaks, which correspond to the pristine product K12, the pristine compound K12, and the reaction imine product number 1 here, as demonstrated shown in the blue line. All these suggest that in the solution, overnight solution mixture of K12 and butylamine, we do have the imine being present. And we also measured TCSPC, which showed that by the reaction mixture overnight showed identical PL lifetime to the amine product. As we had mentioned before, as the reaction rate for K12B is actually slower comparing to K12, when we compare the overnight mixture of K12B with butylamine, we don't see such a good agreement between the absorption spectrum and the absorption spectrum of the amine itself. However, we do notice some of the absorption features starting to emerge when the reaction is taking place overnight, such as the absorption feature around here. And we also notice a redshift in the emission spectrum of the overnight mixture of the K12B and butylamine, suggests that the amine is indeed being formed. We also found an increase in PL lifetime, again suggesting that the amine is actually being formed in the overnight mixture solution. We also want to mention this. When we also measured the PL quantum yield of the synthesized amine product, where we found that the solution PLQY in the K12 amine product is about half of what's in the pristine K12 compound, which explains very well why we see a decrease in PL intensity. Whereas for K12B, the K12B amine product actually showed a much higher PLQY comparing to K12B itself, which explains why we see such a significant increase in in the PL intensity. So all the solution measurement results actually ties up pretty well and can be explained by the formation of the amine compound. However, we did not stop there because primarily for the purpose we want to achieve, in order to be able to detect whether the meat is spoiled or not in your, say, your food container, we want to be able to detect the presence of cadaverine in the vapor phase, but not in the solution phase. So what we did is we spin coat some of the sensing films, put them in a sealed measurement chamber, and injected 10 mils of cadaverine headspace vapor into the chamber to see how the PL intensity and PL spectrum change. By monitoring the PL intensity change for K12 and K12B, we have some rather interesting observations. The first thing we noticed that upon injecting the cadaverine headspace, we have a very rapid decrease in PL intensity for both K12 and K12B, as you can see here. This change takes place within the first 20 seconds of injection of the cadaverine, and we observe immediately a 20% decrease in PL intensity for K12 and a 50% decrease in the PL intensity for K12B. After this first initial decrease, we observe a slight recovery for K12 and then a gradual decrease in the PL intensity falling back to the baseline. And when we look at the PL spectrum, we notice a blue shift and a decrease in intensity for K12, which is actually agreeing very well with what we've seen in the solution. And for K12B, again, we observe a gradual increase in the PL intensity over time, and we observe this as well in the PL spectrum. Again, this is in agreement with what we see in the solution measurement, suggesting that the amine is indeed being formed. However, in the solution, we did not observe this rapid decrease in the PL intensity. And this can be explained by the photoinduced whole transfer causing fluorescent quenching, which is first much faster than chemical reaction, explaining why we see this before the chemical reaction. And also because this fluorescent quenching is reversible. This also explains why we see a weak recovery for the K12 here. And then we move on to test a range of different primary, secondary, and tertiary amines to see whether this fluorescent response is universal to all different amines or not. So what we found is that first we observed this rapid decrease in PL intensity for all the tested amines, suggesting that the fluorescent quenching based on photoinduced whole transfer is actually quite universal for all the different amines we tested. But we also noticed that only with N-butylamine did we observe an increase in PL intensity with K12B film over time. And we also observed the shift in the PL spectrum with N-butylamine as well, which suggests that only N-butylamine is having a chemical reaction taking place at the same time. It's rather interesting actually to notice that for the benzoamine and aniline, both of which are also primary amines, we don't really see any chemical reaction within the 10 minutes we've measured. And this can be due to a number of reasons. Well, where like steric hindrance in aniline might be taking place, and that because of the lower vapor pressure in benzoamine and aniline, which is about 2 orders of magnitude lower than butylamine, the the concentration of the analyte in the film is actually quite low. And also because there is this aromatic group, there's a larger binding affinity between the analytes in the film, which makes the diffusion of the analyte into the film a lot slower compared to butylamine. And for the other amines like diethylamine, triethylamine, and pyridine, we all observe the fluorescent quenching. However, the change in the fluorescent intensity is actually quite proportional to the vapor pressure of the different analytes. In the more volatile analytes, such as triethylamine and diethylamine, we observe quite a strong quenching signal, whereas for analytes with low vapor pressure, such as pyridine, the quenching is a lot weaker. We're also interested in finding out whether this response is taking place with other nucleophilic compounds or not. So we test the fluorescent response to a number of oxygen nucleophiles, such as acetone, ethanol, water, and isopropanol. And none of these compounds showed any pronounced fluorescent change outside of experimental error. And by summarizing all the shown responses in fluorescence, we can plot the change in PL intensity after 1 minute and 8 minutes of analyte exposure, giving you the figure on the left-hand side here. And here we can clearly see that only cadaverine and butylamine showed an increase in PL intensity over time with K12B, which allows us to actually discriminate the alkyl primary amines from all the other amine compounds. And we're also, as we're trying to apply these compounds for practical use in food quality, we want to know that whether they will be responsive to the amine compounds at a low concentration. So by testing with a low cadaverine vapor at low concentration, we can clearly see a PL response for K12 at 1.6 ppm and for K12B at 400 ppb. It has been reported that like some of the markets of fish and sausages have a rather similar cadaverine concentration of a single-digit ppm. Our sensing compounds have demonstrated that they have the sensibility to be used in these applications. So as we have demonstrated, we have sensing compounds which enables a colorimetric as well as fluorescent-based detection. And to further demonstrate the potential in the application in smart meat packaging, which potentially you can just put in a piece of the sensing film inside your, say, your food container and monitor the change in color and PL intensity over time. And so we blended the sensing compounds in with PDMS, and at 0.2 weight%, we have these flexible membranes. And by putting them inside a headspace of butylamine, we can see within 5 minutes, you can observe the change in color for both K12 and K12B. As you can see here. So, okay. So as you can clearly see, after exposing to the headspace butylamine vapor for 3 minutes, we can clearly see a change in color for both K12 and K12B PDMS membranes. And the change in fluorescent color as well as intensity can be easily monitored under the black light, as you can see here. So to briefly summarize, we demonstrated 2 fluorescent high affinity molecules which can be used to achieve amine detection using both colorimetric and fluorescence-based detection mechanisms. We established the chemical reaction between these sensing compounds and primary amines, forming an imine product. And we also observed fluorescent quenching in these compounds with a range of primary, secondary, and tertiary amines. We have a selective response towards nucleophilic nitrogen groups over oxygen nucleophiles, and we can specifically identify alkyl primary amines from all the other amines. We demonstrate a clear response at the low cadaverine concentrations, which is relevant to the food industry, and their potential for being used in a low-cost smart meat packaging is demonstrated. Thank you.
Thank you. Very interesting presentation as well. So we have a question has come through on the chat. So Attila says, are the compounds safe to eat?
Well, I don't think you're supposed to eat them in any case for the smart packaging, but well, the answer would be no, we haven't tested that out yet. But the idea would be that you potentially you would not need them to be in any direct contact with food at all, because you can just stick it to wherever you want, say in your fridge or inside your food container, and just by looking at it, whether the colors change or not, you'll be able to tell whether something has gone off or not.
Yeah. Are there any other questions or comments from the audience? I guess maybe if in case there's no other questions, I might jump in. So yeah, I'm just interested in this application, the sort of the market place for this. I mean, are there other technologies for doing this kind of sensing? Are there any other ways of monitoring? Is cadaverine sort of the standard way of probing the shelf life of meat products?
Apparently, yes. Well, I guess in food industry, they have more advanced ways of monitoring the food quality, obviously. But yeah, I think cadaverine is one of the most commonly used biogenic amine for like spoilage detection. Yep, but then again, we're not trying to compete with, say, like mass spectroscopy or any of those technologies that's already out there, because they would not be practically, applicable in your kitchen or mine. So I guess essentially we want something that's easy, that's cheap, that can be used by, say, anybody. Yeah.
Yep. And you can embed within the packaging. As you said. Yeah. Any other questions? Okay, if there's no other questions, I think please everyone join me thanking virtual round of applause, thanking our speaker one more time. So thank you very much, everyone. So